A student mixes 40 milliliters of 0.1 molar hydrobromic acid with 60 milliliters of 0.1 potassium hydroxide at 25 degrees Celsius. What is the concentration of hydroxide of the resulting solution? So both hydrobromic acid and potassium hydroxide are both strong bases, or sorry, strong acids and strong bases, which means that we're going to assume that we are going to be going to completion. The balanced equation here, we're going to have the hydrobromic acid plus the potassium hydroxide, which will again dissociate completely in our water, and then our neutralization, we have water plus the potassium bromide salt. Any hydroxide that is not consumed and turned into water in the neutralization is going to be what we are interested in, since this again is going to be a strong base, which means that we are going to dissociate almost completely. So we need to figure out the limiting and excess reagent for both. So we have 0.1 molar for both, but we have different volumes here. So the 0.1 molar, but 40 mils, this is the same as 0.04 liters. So the 0.1 times 0.04 gives me 4E3 for the moles of 4E negative 3 for the moles of the hydrobromic acid that is present. And then the 0.1 times the 0.06, which is the same as 60 mils in liters, is 6E negative 3 moles of the potassium hydroxide. Since our reaction is a 1-to-1 reaction, we are going to run out of the hydrobromic acid before we utilize all of the potassium hydroxide. If you take the difference between here, we are going to leave a grand total of 2E negative 3 moles of hydroxide that did not get turned into water. And then we are going to go ahead and divide that by the volume, the 100 milliliters, otherwise known as 0.1. So the 2E negative 3 divided by 0.1, we get 2E negative 2, otherwise known as 0.02 molar, and that's going to be option choice C. The equilibrium for the acid ionization of acetic acid is represented by the equation above. If 10 mils of 0.2 molar acetic acid reacted with 5 mils of 0.10 molar sodium hydroxide, which of the following could be used to calculate the correct pH of the following solution? So we are going to need to figure out what our actual concentrations are, and they are not fully solved out. So we can just go ahead and match based off of our overall reactants and products instead. So we're going to be using the Henderson-Hasselbalch equation, which is that pH is equal to pKa plus the log of the concentration of my conjugate base divided by my concentration of my acid. And so I will identify from here what makes sense. So all of the equations initially pan out, looks good. Just need to go ahead and see what will match. So my top is going to be my concentration of the conjugate base. The conjugate base is going to be the acetic acid after it has reacted, and that will be the 5 mils and 0.10 molar. and that being divided by the initial concentration. Since this is a 1-to-1 reaction and we do have less of the sodium hydroxide, we are going to be left with more of the acetic acid. And we're only going to be able to react the amount of moles of sodium hydroxide that we have present here. So initially we have the 0.2 divided by 0.01, which is 0.002 moles of the acetic acid, and then we're only able to react the 10 divided by 5 moles, or 0.05, which is 0.0005, and that's going to be the number of moles of acetic acid that can actually be used in this equation. So that's 0.0015 moles of acetic acid, and we have a total volume of 0.015 liters present there, and that's going to be our total volume. So when we are dealing with the conjugate base portion, we are going to be dealing with just the amount that could be utilized from the sodium hydroxide, since that's the limiting reagent, divided by the total volume. And so that is going to be exclusively answer choice C. We could just eliminate that down just because of this initial portion here. For the acid portion here, you can see that we have that differential being taken into effect, where we are seeing the limiting in excess over the total volume here. So option choice C is the only answer choice that matches the restraints that we have. A solution containing hydrochloric acid and the weak acid, chlorous acid, has a pH of 2.4. Enough potassium hydroxide is added to the solution to increase the pH to 10.5. The amount of which of the species increases as the potassium hydroxide is added. So as we go ahead and add potassium hydroxide, we are capturing the hydrogen ions, and so those are going to be reduced there. And we are slowly basically capturing all of the hydrogens that are coming off of the chlorine, which will remain the same concentration since it is a strong acid, so that's going to remain the same. But we are not going to be able to change our overall amount. We're not shifting the reaction here to make the weak acid go back into its normal state. Instead, we are removing hydrogens, and so we are shifting and causing that weak acid to go ahead and dissociate more readily, and therefore increasing the number of chlorite ions that we have present within the solution. Acid dissociation constants of two acids are listed in the table above. A 20 milliliter sample of a 0.10 molar solution of each acid is titrated to the equivalence point with a 20 milliliter sample of a 0.10 molar sodium hydroxide solution, which is a true statement about the point. So I'm going to look at the Kas of both of these acids, and I can see that the Ka of solution 1 is substantially lower than the Ka of solution 2, which does mean that this is the stronger acid and this is the weaker acid. So I can go ahead and eliminate anything that states that solution 1 is going to have a be whatever because it's a stronger acid, because we know that that is the weaker acid. So we are now between whether it is a higher or lower pH based off it having a stronger conjugate base. And the stronger the conjugate base, the higher the pH is going to be, because the lower the concentration of hydrogen ions we have present. So option B is going to be our best answer choice. The net ionic equation for a reaction that occurs during titration of nitrous acid and sodium hydroxide is. So nitrous acid and sodium hydroxide. Nitrous acid is a weak acid, which means that we are not going to dissociate readily. And so on the left-hand side, we should see nitrous acid just written out present. So I can go ahead and eliminate C. And then sodium hydroxide are going to dissociate fully. However, sodium is an alkali metal, which means that it is always going to be soluble, so I should not see sodium on either side, since this is a net ionic equation. Then we don't see where we're going to see the hydroxide still, because that is going to turn into the water. We're not going to initially have water. We have the sodium hydroxide dissociating into sodium and hydroxide, and so we will see them separately. Addition of sulfurous acid, which is a weak acid, to barium hydroxide, which is a strong base, results in the formation of a precipitate. The net ionic equation for this reaction is, so we should see something plus water on the left-hand side, so we can go ahead and eliminate A as our answer choice. And then we know that sulfurous acid is a weak acid, so we should not see it dissociated on the left-hand side. And then we know that the barium hydroxide is going to go ahead and fully dissociate, since we know that it is a strong base. So that leaves us with B and D as our only answer choices here. And so I'm going to go ahead and look and see that only B has a precipitate formed, which was what I was told was going to happen. So answer B is the only answer choice for question 7. A solution prepared by mixing 10 milliliters of 1 molar hydrochloric acid and 10 milliliters of 0.12 molar sodium hydroxide has a pH of. So this one, you don't actually need to do any math here. Sodium hydroxide and hydrochloric acid, when they react, it is going to be a 1-to-1 reaction. So we're going to have HCl plus NaOH going to water and sodium chloride. And this is balanced, so this is 1-to-1. We can see that we have equal volumes, but not equal molarity. We do have slightly more sodium hydroxide than we have hydrochloric acid, and so that means that we should be basic. So you can eliminate anything that is not going to be basic, and then between these two, we are left with 0.2 moles of sodium hydroxide. And so the negative log of 0.2 moles, sorry, it's we have 0.2 moles left in 20 mils, which is 0.2, so 0.2 divided by 0.2, so 1. So negative log of 1 gives me, it's going to be 0.02 for my number of moles that are left, and then divided by 0.2. So that's 1e negative 1. So then negative log of 1e negative 1 gives me 1. And so we know that pH is equal to 14 minus the pOH, which is what we just calculated here. So 14 minus 1 gives me 13. When 200 milliliters of a 2 molar sodium hydroxide solution is added to 500 milliliters of a 1 molar hydrochloric acid solution, the pH of the resulting mixture is going to be closest to. So again, we have hydrochloric acid and sodium hydroxide. So same reaction here. We're just going to go ahead and figure out the number of moles that is going to be present here. So we have 2 moles per liter, and then we don't actually have a full liter. We have 200 milliliters, and so that's going to be 0.2 for the 200 milliliters times 2. So we have 0.4 moles of the sodium hydroxide, and then we'll have to do the same thing for the hydrochloric acid. So 0.5 times 1 here is going to give me 0.5, obviously, so 0.5 moles of the hydrochloric acid. And we can see that we have more hydrochloric acid than sodium hydroxide, so we should be acidic. So we can go ahead and eliminate any answer choice that is not acidic. And then we're just going to be between 1 and 3 here. We can see that the difference between these is going to be 0.1 moles of hydrochloric acid that I have present, and then we have a grand total of 700 milliliters, so that's 0.7. So 0.1 divided by 0.7 will give me the concentration in molarity of the hydrochloric acid, which since is a strong acid, will dissociate fully. Then just the negative log of this number gives me 0.845. This is in scientific notation, so just careful here. E-1 means that this is 0.845. And then we know that pH is going to be equal to 14 minus, or sorry, no, it's not. pH is just going to be equal to that 0.08, which is going to be closest to answer choice A or 1.